Okay, next section is on triple integrals. This is 14.6. I hope you could hear me. Stupid microphone was over across the desk. Triple integrals. Right. So, how the heck? What the heck are these? What are we doing? It's mainly just one step up from the double integral. So before, in order to find area between two curves, in Calc 1, we would take the difference of the curves and integrate that from some point to some intersection point to some other intersection point. And then in Calc 2, we learned we could kind of embed these two functions into an iterated integral on the inside there. So we would go from curve to curve on the inside, and then replace this with just have a 1 basically, and then we would have dy dx, okay? And that would equal the area. Okay, now, and as you've probably seen here in the book, we have these double integrals to find volume. And basically in here we would have some sort of surface. Okay? But you can always think of that surface as, or the innards of this integral as the difference between the surface h and basically the xy plane, which is another surface, 0. Okay? You can embed this idea then into another iterated integral, another integral inside. So you have the integral from a to b, and then g of x to f of x. And then inside here you can put 0 to h of xy, and then have dz, 1 dz, dy dx. Okay? And it's just another way to get volume. So this would be volume, which we could do with a double integral, but this integral is nice because now we can attach ideas or numbers to the volume elements. Okay, so in particular, the visual picture of this, which we'll talk about in a little bit, will be kind of summing up the volumes of a bunch of little cubes, and then on each cube, this function in here will if it's 1, it'll just end up giving you the volume. But if it's any other function, it kind of gives you a fourth dimensional number, right? So you could put a function in there for density, and then if you have an object that is dense, more dense in one region than another, you could use this to evaluate it. One problem I remember, we had a chemist in our class a couple of years ago, and he was working on temperatures of these bags of fluid, you know, and he would need to know the temperature, and you know, in different parts of the bag, the temperature was different. And you'd have to use these triple integrals to kind of, with a function that told us the temperature of the liquid in the bag at different places, right? So he would use triple integrals to kind of figure out the overall temperature of the bag or something like that. Okay, so you can think of or imagine your own applications, but I don't know, I'll shut up. All right, so anyways, the way I want us to think of this, to remember it, and maybe other people have different, other teachers will have different ways. I always think kind of as a generalized Riemann man running through. And this isn't literally what they're doing. The Riemann man is literally kind of just adding up a bunch of cubes in a nice order. But I think of it as going from surface 1 to surface 2. So a bottom surface to a top surface. So maybe I should even put that bottom surface to top surface, and then bottom curve to top curve. And then left point to right point. And that's all dependent on your orientation, right? So if my running man was going up the y-axis or something like that, you would have to say the bottom point to the top point again. Okay, but that's the idea, and then you'll have some now three-dimensional function inside here. If it's just one, it gives you the volume, but otherwise it'll be some volume increment afterwards. You know, the volume of a cube is length times width times height. So you'll have dz, dy, dx, or some variation on that. Okie dokie. Let's try one. So this is problem 13 in the old book. And we have a solid in the first octant bounded by coordinate by the coordinate plane. By the coordinate plane and the plane z equals 5 minus x minus y. So first octant, the xy plane, and the plane z equals 5 minus x minus y. The coordinate plane, sorry. I think what they mean is just stay in sort of the room designated by the positive x, y, and z axes. And between this region here and this region here, to graph this thing, you kind of let two variables equal 0 and then get the z-intercept. So let x and y be 0 to get z is 5. Let x and z be 0, and you get y is 5. Okay. And then let y and z be 0, and solve that, and you get the x-axis intercept, right? So x is 5. Okay. And then if you kind of connect the dots here, you want to know the region underneath this thing inside in this one octant. So it's basically just this triangular solid region that we're trying to find the volume for. Okay. Okay, so for volume, you need not put anything inside your triple integral. Okay, so in here you just put a 1. And then we have some ordering. It depends. You could do any ordering you want. Usually dz, dy, dx is kind of our traditional ordering. Okay. So surface to surface, in order to pull that off, z equals something to z equals something. So z equals 0 is the xy plane here, right? And then you want to go from that surface to the surface that's on top. So this is like the floor, and then you want to go to the ceiling. So the ceiling is this triangle right here, which is given by this plane here. Okay? And that's what I mean surface to surface. So I'm going from this side to this surface. And you could do other ones, right? You can take this back surface and then go to the red surface. You take this other back surface, go to the red surface. So if you went from the back surface, that would be the dy. So you would be going y equals this, and then you'd have to solve this for y, right? So it'd be y equals 5 minus x minus z. But if you're doing it in the orientation we are describing, you're going to go from z equals 0, which is the xy plane, this green part, to z equals 5 minus x minus y, which is that red triangle region. Okay? So you think of it that way. You're going z equals bottom surface to z equals top surface. And then you're going y equals bottom curve to y equals top curve. And then you're going x equals first point to x equals second point. Okay, so we got the surface part done. Now we need the dy dx. And for that, I sometimes just draw an XY plane here. And this is basically this green plane, this green triangle is what I'm after, right? So in particular, then I can plot those 2 points I got, 5, 0 and 0, 5 in the XY plane. It's the standard kind of orientation. The Riemann man is going in that direction. So I'm going from y equals 0 to y equals that line. Right? So y equals 0 to whatever that line is. It has intercepts at 0, 5, and 5, 0. So the equation is going to be y equals 5 minus x. Okay? And you can check to make sure, right? So when x is 0, y is 5. Sorry. When x is 0, y is 5. And then when y is 0, x will equal 5. Okay, okay. So it works. However you get that line, you may have to, okay, so it's like y equals mx plus b. You know the intercept b is 5, so y equals mx plus 5. And then you know a point is 0, 5. So you can plug 0, 5 in here and get 0 equals, or 5 equals, well, you need to plug in 0, 5, 0, sorry. So plug in 5, 0, and you get 0 equals 5m plus 5. And then you could solve for m, and you get m is negative 1. Okay, so plugging all that together, you get this, just in case you've forgotten how to figure out the equation of a line. It's in there. Okay, so, right. Okay, so the top bound here will just be the y equals 0, this line, to y equals 5 minus x. And then finally, the running man is going from 0 to 5 on the x-axis. Okay. Okay, and that's kind of the setup, and then you would just integrate that triple integral. So maybe we should, well, we'll integrate the next one. Let's just skip to the next one. Okay. Okay. So number 19 is another find the volume. And this region is a bit more complicated. It's given in the book. It's drawn out in the book. I'll attempt to draw it here. Okay. And they messed with the XYZ axes. So this is now the y-axis. This is the x-axis, and this is the z-axis. Okay. And the xy plane will have a parabola, x equals 4 minus y squared. And so the intercept's at 2 and 2. And then it goes out to 4. Okay. And then it has this plane z equals x, and that looks like the following. Okay. And then they want you to find the volume of this thing. That looks like some weird pump type deal. So I had a foot pump that looked like this once for a raft. Okay, so again, this line in the xy plane, this curve in the xy plane is y equals 4 minus x squared. Oh, sorry, other way around. It's x equals 4 minus y squared. This red plane here, the one I put in red, is z equals x. Okay, and then the xy plane is z equals 0. Maybe the book says that. Okay, I need to find the volume of this region. And so I'll have my triple integral. And I'll go in the traditional dz, dy, dx ordering. Okay, and you're thinking surface to surface. So the floor surface is this kind of parabola down here. Okay. And then the ceiling surface is the z equals x. Okay, so I want to go from that surface to this surface. Right, so z equals 0, which is the xy plane, to z equals x, which is the red surface. So so far so good. And then I want to go from y equals to y equals, so curve the curve, or some variation on that. Okay, so in the xy plane, we have this figure, okay? X equals 4 minus y squared, which is this curve here. We have to do some rotating and stuff to get it into our traditional ordering. And then if we do dy dx, we're going to have to split this into two branches, right? Because this will be the top branch and this will be the bottom branch. So you know what? Let's not do dy dx. Let's do dx dy. That way we can go from, we'll have the running man in this orientation like this, and I'm going from this curve to the parabola curve. Okay. So this curve right here is x equals 0, and then this curve here is already given in its form, x equals 4 minus y squared. Okay. And then the Riemann man is going from -2 to 2. Okay. And then it's just a matter of integrating this thing. So let me rewrite it with all this, without all the scribbling. So I have dz dx dy. And I want to integrate it, right? So first, with respect to z, I have a double integral of z, and I have to evaluate it from 0 to x, dx dy. So plugging in x, I'll have x, and plugging in 0, I'll have 0. So x minus 0 is x. Okay, so one integral done, 2 to go. Okay, now integrate x with respect to x. So that gives me x squared over 2. I have to remind myself to evaluate. Okay. Then I'm plugging in this expression into this expression. So I have the integral of, and I'm going to pull out the 1/2. That may make life a little bit easier. And I have 4 minus y squared squared minus, if you plug 0 into that, sorry, I went off the page. So what the heck did I do? I pulled out the 1/2. I put 1 over y. Okay, so plugging 4 minus y squared into here, I get 4 minus y squared squared right here, all over 2, but I pulled out the 1/2. Okay. And then if you plug 0 into there, you get 0, so minus 0. And then dy. Okay, I'm going to go ahead and FOIL this out. So this will be 1/2 integral of 16 minus 4y squared minus 4y squared is minus 8y squared plus y to the 4th, and then dy. And then I have to integrate that with respect to x. So I get 1/2 times 16y minus 8y cubed over 3 plus y to the 5th over 5. And then I need to evaluate that from -2 to the 2. Maybe easier to redistribute the 1/2 to clean it up a bit. So I'll have 8y minus 4y cubed over 3 plus y squared over 10. Yeah, that didn't really help very much, but there it is. When I have a bunch of fractions, I like to factor out the fraction. It looks kind of weird, but it sort of turns everything into a problem in the integers. So it's probably what a calculator would do. I think it looks weird, but it helps. So what did I say? I'm going to pull out 1/30th. Okay, believe it or not. And then on the inside, I'll have 240 y. Maybe this doesn't help very much, but yeah. Minus, what is it, 40 y cubed plus 3 y squared from -2 to 2. Yeah, that's not very helpful, but we can go ahead now and go to our calculator, which I don't have on me, and evaluate this thing. I guess I could do it by hand, but all right, sure, why not? So 240 times 2. 240 times 2 is 480, minus 40 times 8, right? So that's going to give me 320, plus 3 times 4, which is 12, and then minus -2 times 240 is another 480, and then -8 times -40 is plus 320, and then plus another 12. Okay. And then this will be 1/30th times, well, it looks like we're kind of blessed in some regards. The answer is not negative, Dave. So what did I screw up? Oh, this guy back here, it's y to the 5th. So that screws things up a bit. This will be 3y to the 5th. And then 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 3 is 96. So this will be 96. And then this will be 96. That's not what's bothering me, right? Oh, this is -480. Well, that'll change things, right? Okay, so 960. These guys seem to cancel out. And minus 640. So 96 minus 64 is 32. So 32/3, really? That don't sound right. Well, I don't know. I don't want to spend a half hour on this one problem trying to figure out where I went wrong in the math. And it's all because I decided to be cool and clever and factor this thing out. You know, if I hadn't done that, I'd be in line with my notes. So don't try to show off in front of anybody, okay? All right, so what the heck did I do wrong? This is 3 divided by 24 has to be 8. 16, yeah. This will be 40/30, which is 4/3. 3/30, which is 1/10. 480 minus 480. 960 minus 640. 320. 32/3. This is plus, so it'll be minus. Oh, and then this will be minus. There it is. Crikey. So 96 and 96. I think it was 96. I can't read my writing. So 5, 2 to the 5th. 2 times 2 is 4. Times 2 is 8, times 2 is 16, times 2 is 32, times 3 is 96, times another 2, 12, 1, 18, 192. So is that minus? No, it's plus 192. So 960 plus 192 2, 15, 9, 10, 11, 1, 1, 5, 2, minus 640 is 2, 1, 5, 12, all over 30. 5, 12 divided by 2, 2, 4, 1, 1, 5, 6, 2, 5, that's it. 2, 5, 6, all over 15. My apologies. I hope you fast forwarded. But there it is. Okay, next. Sketch the region. And these problems now, they'll start giving you ones where you have to rewrite the order. And these can be kind of a nightmare scenario, but it's not bad practice for playing around with these integrals. So let's take a look. Sketch the region and then rewrite the order. In this case, we want to go dy, dx, dz. And we're starting with the integral given in the book. 29 is the triple integral of dz, dy, dx. And we're going from 0 to 12 minus 3x minus 6y all over 4. And then 0 to 4 minus x over 2. And then 0 to 4. Okay. So I'm going from z equals this surface to this surface, y equals this curve to this curve, and then x equals this point to this point. So let's figure out what that region is. Z equals 12 minus 3x minus 6y over 4. To figure out what this plane is, you do the x, y, and z intercepts. So you let x, y equal 0, get the z intercept. Let x, z equal 0, get the y intercept, etc. Okay, so the x, y intercept, you're letting, oh sorry, for the x intercept, you're letting y and z be 0, so you have 0 equals 12 minus 3x over 4. So that'll be 0 equals 3 minus 3/4 x. So 3/4 x equals 3. Multiply both sides by 4/3. So x is 4. For the y-intercept, let x and z be 0. So you got 0 equals 12 minus 6y over 4. In other words, 0 equals 3 minus 3/2 y. In other words, 3/2 y equals 3. In other words, y equals 2. And then for the z-intercept, it should just be 12 over 4. So z equals, I guess, 3 again. Okay. Okay, so let's get a picture of what we're dealing with here on the XYZ plane, or the XYZ space, sorry. X is 1, 2, 3, 4. Y is 1, 2. And then Z is 1, 2, 3. Okay, so it's this triangle type situation again. So going from surface is Z equals 0 is the XY plane. And then to Z equals 12 minus 3x minus 6y over 4 is this triangle. Okay, I need to change the integral into dy, dx, dz. So in order to pull that off, I go surface y equals to y equals. So this is x, this is y, and this is z. I want to go from y equals 0, which is this back surface here. Put that in blue. Oh, frick. It's just this triangle. So I'm going from this surface here, this back surface, to this triangle region up front. So then it's going to this surface here. Okay. So y equals 0 to y equals this thing here. How do I get the formula for that thing? well, you just solve this thing for y. Okay? So taking this guy and solving it for y, I get 4z equals 12 minus 3x minus 6y. Add the 6y to the other side, so 6y equals, we'll subtract the 4z over, 12 minus 3x minus 4z, and then divide by 6. So the red surface out in front, you can rewrite as y equals 12 minus 3x minus 4z over 6. Okay? And that'll be the upper bound on this first integral on the inside. So 12 minus 3x minus 4z all over 6. Okay? And then you go to work in the xz plane, right? Because that's going to be your leftover variables now. So I have an x equals some curve to x equals some curve, and then z equals some curve to z equals some curve, z equals some point to z equals some point. So the orientation here is in this direction. Okay. And to get the curves in the xz plane, you can use these intercepts, right? So one point will be 4, 0, the other point will be 0, 3. So 1, 2, 3, 4, 0, and then 1, 2, 3. Okay. And this orientation going curve to curve, I'll go from x equals 0 to x equals this line. Okay. So in terms of x, it would be z equals, you could get the slope, right? It's intersect with the z-axis will be at 0, 3, so plus 3, but its slope is down 3 over 1, 2, 3, 4. So down 3 over 4 for the slope. And then you'd have to solve this for x. It'd have been easier if we just did it in the other orientation. I totally apologize. So put x on the z-axis and z on the x-axis. Because now I'm going to have to solve for x, right? So anyways, negative 3/4 x, or maybe plus 3/4 x equals negative z plus 3. Just move the z over, move this over, and then multiply by 4/3. So x equals negative 4/3 z plus apparently 9/4. Seems like I screwed something up. Down 3 over 1, 2, 3, 4. So down 3 over 4. And I move this over, then I move that over. Then I multiplied by 4/3. Oh, it's right there. Sorry. So 4/3, that would just give me 4 here. Okay, sorry about that. Okay, so I'm going from x equals 0 to x equals negative 4/3 z plus 4. Right? And then on the z-axis, I'm running from 0 to 3. Okay, we won't integrate that. Let's just leave it there. All they want us to do is sketch the region and change the order. Okay, now we want to go and think about sort of the Riemann man with regards to these triple integrals. And along the way, we're going to be maybe applying some function to each one of the little cubes that we're adding up. So the triple integral over a solid object, which we'll call Q. So you kind of recall how this pans out. And in the first case, we were with double integrals. We were integrating over a region, okay, and this was cut up into a bunch of little change in x's and change in y's. Okay, and so at some point in here, we could associate with it a function, and then the Riemann man would be adding up a bunch of volumes in that regards. Okay, but if you didn't associate a function with it, it would just be finding area, right? So the area of this particular rectangle, a sub I, would equal delta x sub I times change in y sub I. And then if we wanted to be ambitious, we could, and let's call this delta a sub I. So the Riemann man is adding up all these little deltas. If we want to get ambitious, we can attach a function to this, and what the Riemann man is then adding up is a volume, right? So in that case, it would be f of x sub I comma y sub I, where I'm inputting this point x sub I comma y sub I into some function, which can represent anything you want, and then multiplying it by the area, and that would give me the volume of some rectangular solid, and that's kind of what our double integral is doing. So this double integral would in fact give you a volume, right? And this would just be the limit of the sum of these things right here. Okay. We never made it clear with regards to the Running Man, but if you do look in some other books, they'll use double sums to kind of finagle that question. And you'll be sort of integrating, adding up these guys, and then adding up these guys, and then adding up these guys. Okay, so that was double integrals. So we're just remembering all that information. Now, instead of using rectangles as kind of our basic objects, so in one dimension we just use intervals, in 2 dimension we use rectangles. Now in 3 dimensions with the triple integrals, we're going to be adding up a bunch of cubes, okay, or rectangular solids. So now the little things that we're adding up in whatever region you're dealing with. So again, we have, you know, our x, y, and z. And leave a little space so I can kind of populate it. We'll have to go through and kind of section this up into a bunch of cubes. Okay, and find the volume of all these little cubes inside some region. So the region I've chosen is just kind of a rectangular region. And so in particular, we sort of consider just one particular element. So back here, our elements were all boxes. Now all of our elements are going to be little cubes. And we'll have little delta v's, which will be delta z sub I times delta x sub I times delta y sub I, which would be just be like this, right? And then if I summed all those up in a Riemann sum, I would find the volume of the region. But we're going to be more ambitious, right, and attach another factor to it. And then maybe we could call this delta f sub I for 4th dimension. We can attach some, maybe like I said in the previous section, a temperature value to every xyz point in space, and then multiply it by this volume increment. Okay. So for every little cube, if you're talking about temperature, maybe you could apply a function to the middle of those points, and then evaluate that, and then add through the entire thing, kind of. When we go to our triple integral and our Riemann man goes ahead and he adds up all these 4th dimensional values and then takes the limit of it, it's going to look like this: a triple integral over a solid region Q which will equal, sorry, you'll have this f function in here, x comma y comma z, and then times the volume increment. Okay? And we call this the triple integral of f over q. Okay, okay, but it's just a higher dimensional case of what you've already kind of been doing. So in one dimension, in one dimension, your little change in widths are just on the x-axis, so you would have a change in x here, and you could, if all you're doing is integrating 1 dx from a to b, what you get is a length here on the number line. So if you go from a to b and you integrate this thing, what are you going to get? You're going to get x from a to b, and then if you subtract b minus a, you get the length of that interval, right? And the next dimension, if you now work with your little change in x's, they'll become change in a's, which will be these things. And then if you integrate the function 1, what you're going to end up doing is just finding the area of this region. Like back here, all you did was find the distance of this length. Right? Then you go up another dimension, and what you're doing, your basic element, so back here, again, it was a length. Here it was an area of these squares. Now it's a volume of a cube or a rectangular solid. If you just put 1 in here, you would end up getting the volume of this object. Okay? But what we're going to do is describe a function, and that will give us a fourth dimensional sort of measure. Okay, so hopefully that makes some sense. When you're working with the limits in this section, there is, again, this idea of a norm. Back here in area, the norm was the length of the longest diagonal. And here the norm will be the length of the longest diagonal of the cube. So you have a cube here. Let's see if I can draw it. I don't know. So here's my floating cube. It's the distance from maybe this point to this point here. And that would kind of be your norm for your delta v's. And then to go from your limit to here, you let the norm go to 0. Okay. Okay. So there's all that business, hopefully taken care of. There's applications in 3 dimensions with regards to centers of mass and moments of inertia. I probably won't beat you up too much over this. We'll just take a look at the formulas and how they change once we get to solid objects as opposed to plates, which were more or less 2-dimensional objects. So center of mass and then second moment. Okay. If you remember the center of mass in 2 dimensions, we use the axes as kind of our fulcrum points. Now what we're going to be doing is using planes, xy plane, yz plane, etc., as our balance points. So again, before, in even 1 dimension, what you're dealing with is a teeter-totter with a fulcrum on it, and maybe you have some objects with different masses on the teeter-totter. Obviously, it's going to be going in this direction, right? So the moment of this thing would be the sum of the masses times their distance away from the fulcrum. And you could kind of standardize this in the 2-dimensional xy plane such that you consider the y-axis as your fulcrum. Okay. Okay, so the moment in general with regards to the y-axis is going to be the sum of the masses of the individual pieces times their distances from the x-axis. And then you can play the same game with the fulcrum about the x-axis. So that becomes your fulcrum, and you're teeter-tottering like this. Okay. In that case, it's the sum of the masses times their distances away from the y-axis. Okay, so this is really in 2 dimensions now. For continuous objects, this became the double integral of x times rho of xy dy dx, or whatever, we'll just say dA. And then this thing becomes the double integral of y times rho of xy dA. Okay. For our new formulas now in 3 dimensions, what you're after is distances away from planes. Okay? So in particular, let's say I have this floating cube. I'll project it into the xy plane here. Okay. So there's some point on the middle of the floating cube, and we find the distances away from the particular x, y, and z planes. Z plane would be this distance to here. You pretend the projection of the cube is right there. The distance from the xy plane would be this distance. And you can kind of read off what those distances are, right? This distance right here is z. This distance right here will be y. And then its distance to the yz plane back here, well, that distance is clearly just x. Okay? So you'll have these new moments. The moment about the, I don't know, xy plane is the z distance. So you end up with a triple integral over whatever solid object you're worried about of z times your rho, and your rho function will now be xyz dv. And then your moment about the xz plane will be the triple integral over the solid object. And again, xz plane is right here, so this distance is y. And then finally, your moment about the yz plane, that'll just be x. Right? Okay. For the mass, it's just the triple integral over the object of so we always need the total mass in order to compute the center of mass. So the total mass will just be the triple integral of the density function, which is, it basically just comes down to finding the sum of the density times the volumes, right? And that will give you the total mass. Okay, so x, y, z, then your coordinates for your what do they call it, centroid, your center of mass will just be obviously m, y, z divided by the total mass, and then m xz divided by the total mass, and then m, what's the other one, xy divided by the total mass. It's no big deal. The moments of inertia, the second moment then, is kind of a little bit different than what we did for 2 dimensions. What we did for 2 dimensions was kind of just slap in so this is part B, the moment of inertia. I think my pen's starting to run out of ink. The 14.4 version, we were able to just build our integrals with x squared, y squared, and z in that fashion. So the moment of inertia about the x-axis would be the sum of the masses times y squared, and then the moment of inertia about the y-axis would just be the sum of the masses about x squared, right? The way it's going to work now is we are concerned with distances from the axes of a solid object, right? So again, if we have this one floating cube to inspect, and let's say its projection is right here into the xy plane. So here is my cube. Right. I need to get the distances of this cube from the particular axes that we're worried about, and then square that. Okay. So it's not just going to be the triple integral of rho times y squared, for instance, for the moment of inertia about the x-axis. And instead, what I'm going to have to do is use Pythagorean theorem here. So if this is the x-axis, and I'm worried about I sub x, I need this distance here, this hypotenuse distance on this right triangle. Okay. So what is that distance? Well, this distance here is a y. This distance here is z. It's getting a little busy in here. So use Pythagorean theorem to get this distance here. So this distance, I'll call, I don't know what to call it, d. D squared is equal to z squared plus y squared. So of course the distance I'm after is the square root of z squared plus y squared. Okay, so when I go to my moment of inertia and plug that distance in, I have to then square it. Okay, so I'll have a triple integral over the solid region of this thing squared, and when you square a square root, the square root goes away, so you end up with just z squared plus y squared dv. Okay. And then the moment of inertia about the y-axis, and I forgot my rho, sorry, and then times rho of x, y, z, dv. Okay, and then this guy, triple integral over the solid region of kind of x squared plus z squared of rho of x, y, z, dv, etc. Right? So I, z is the triple integral over this region of, or the solid object of the other two variables, x squared and y squared, times rho of x, y, z. Okay, and then it's just a matter of plugging and chugging. We'll leave it there for this video and call it quits. Thanks for watching.